Hello, my name is Mike Hickner. I'm an associate professor and the Corning Faculty Fellow in the Department of Material Science and Engineering at Penn State. And what I'm going to tell you about today is our work on 3D printing of patterned anion exchange membranes. So membranes are ubiquitous in energy and water applications, from fuel cells to flow batteries to electrodialysis and also reverse osmosis, where we can either store energy, convert energy, harvest salinity energy gradients, or purify water through the use of these membrane materials. And you can see examples of all of these on this slide. What we did in this work is that we used solventless patterning of membranes using DLP stereolithography. So DLP stereolithography is a form of 3D printing where you use an electronic mask in order to pattern photoreactive mixtures of polymers. And so as you control the exposure and the pattern of the light, you can solidify this liquid polymer precursor into patterned surfaces as shown in these schematics. And so when we made these patterned membranes, what we observed is that the patterned membranes always had lower resistance than flat membranes of the same composition. And so you can see in this plot that the resistance of the patterned membranes is lower. And what we did in the publication listed below is that we developed a mathematical model to account for the parallel resistances between the thin and thick spots of the patterned membranes in order to predict this lower resistance. And this gives us a design tool that we can use to engineer different membrane surfaces. This slide shows the chemical composition of these membranes. So we use PEG dimethacrylate and diurethane dimethacrylate, and we vary the ratio of those photopolymerizable prepolymers in order to vary the hydrophilicity of the membrane. And then we use vinyl benzyl chloride, which is incorporated into the network as a reactive handle, where we can turn that benzyl chloride group into a quaternary ammonium group to turn this hydrophilic network into an anion exchange membrane. So you see a schematic of the final chemical composition of the membranes once they're quaternized on the bottom, and some examples of the patterned surfaces that we've made. Recently, we've been working on pH color responsive membranes, and so as printed, these membranes are yellow, and if we incorporate an indicating molecule inside the network, when we expose the yellow membranes to high pH for 1 minute, they turn green, and at long times, the membranes turn fully blue. So this different shades of green as a mixture of yellow and blue might tell us about the water that the membrane is treating at that point. It might give us some diagnostic capability that's built in to the membrane structure. So finally, I'd like to acknowledge my research group at Penn State, and you can find us at Hickner Group on Twitter. I'd also like to acknowledge our sponsors, including the Department of Energy and the National Science Foundation, and our local organizations at Penn State, the Materials Research Institute and the Penn State Institutes of Energy and the Environment. Finally, I'd like to acknowledge Arkema for sponsoring our additive manufacturing lab at Penn State and the Department of Material Science and Engineering. Thank you very much.